So formal methods provide you an opportunity to unambiguously describe these requirements, and this is really based on the fact that you're using a formal model, a model that has to adhere to certain formal rules that are founded in kind of mathematics. So this makes it way more unambiguous for these requirements. It also, as a result, enables precise communications between the engineers. These rules are very strictly defined, so there is really no ambiguity in the communication between the engineers. Yeah. Furthermore, it will provide verification evidence such as consistency and accuracy, but also compliance. So part of your verification activities are really captured by these formal methods. And then, of course, you can actually also demonstrate some of the system properties. So freedom of exceptions are being generated, freedom of deadlock, isolation between different level but also different modules, worst case execution time, etc. So if you look at the benefits, again, you get an improved requirements definition, just because you kind of you get rid of the ambiguity that you may have in requirements, and as a result you get reduced errors and more errors detected. You actually use these tools, these formal methods, to analyze these requirements in depth, and as a result detect more errors and get rid of more errors. But also by you formulating this formal model, you get forced into thinking about requirements a little bit more, and as a result errors are less prone. So as a result you get increased confidence in the safety properties, increased confidence in highly complex systems, improved quality in error-prone areas. So areas that are areas within modules or modules that are typically error-prone, they actually get better as well. And of course, the nice thing about formal methods is that because of the use of a formal model, it's very you can actually really get good tools to help you. Of course, that would mean reduced cost, and you can actually maintain your software a little better. The challenge, of course, is the lack of education. Since you need to, specify requirements in a real formal way, like by using, some kind of language, some kind of specification language. You find out that there's not that many people out there that are well versed in doing this particular task. So, as a result of that, it's kind of like math. Math is necessarily not, there's a high fear factor associated with math, that you want to have to look at if it's a lot of math involved, you say, hey, it may be very complex. Same thing here, these formal models may look very intimidating. Yeah. So, and that's just the reason for that is just that people don't know how they work, they don't have any experience with it. Whilst formal methods can also not really apply to all problems, and it's really difficult if you have to mix formal with not so formal methods. So as a result of the first item, there's really only a very limited number of formal experts available. It takes a little bit of education regarding the language or semantics or syntax used for these formal models. So that results in kind of a lack of formal method experts. There is, of course, formal method, but there's not that many of them. So formal methods, if you want to do the proof, this can be resource intensive, so you have to kind of realize that. And in some cases people make false assumptions about testing. So there's a variety of activities mandated by ee6083, and of course in some of those, like I said earlier, the formal methods may play a role, and I think I have that on the next slide. So again, this slide 12 is really kind of a summary of what I saw over in the past couple of slides. Okay, so an important portion is, if you go look at these activities mandated by ee6083. So we have system requirements, we take the software specific requirements and turn them into high-level requirements. Then we kind of work out way more detail. We're going to get an increased level of detail by defining a software architecture and low-level requirements. And from these we can derive the source code. And of course the source code we can use in the compiler and linking instructions. We can get executable object code. At the same time, you get all these errors back, which are the integral processes. These are the verification processes. Yeah. So you see there's a lot of errors going back between these individual life cycle blocks that you see here. And of course, for a lot of these, like the ones indicated by black or these, you can actually use formal methods can really be helping you out. Yeah, so in essence, if you look at this slide here, it states this. It says, okay, the formal analysis can be used to satisfy many of the verification activities. Sometimes complete, of course, only partial in the other way. So it's not it may not necessarily be a complete solution for all your verification needs. Yeah. Example on the right. This is kind of a slimmed down version of the complete activities mandated by D178C. Here it says, okay, these are potential or possible paths that you can actually use for verification that can be held by formal methods. Now, if you look at the objectives, again, just like we saw in D178C, the supplements also provide you with tables of objectives. And what's really interesting to see, if you, for example, look up the verification of outputs of the software requirements process, you see the typical first 7 objectives that we already saw in D178C, but added to that are, a set of objectives that relate specifically to formal methods. For example, okay, the formal analysis case and procedures are correct. The results are correct and discrepancies explained. In other words, we came up with a formal model, and then we analyzed the formal model, and there may have at the results section, the results may have been that there are some discrepancies, and of course you need to make sure that you explain those. Yeah. So this is for outputs of the software requirements process. Same thing is of course valid when you go to the design process or the low-level requirements computer architecture, the coding and integration process, and of course also the verification or the coverage analysis. And I'll talk a little bit more on the next slide. Yeah. So in other words, I can actually use the formal methods tool to help me out in the verification processes, either fully or partially. Okay, now one thing to realize is that formal methods are really complementary to testing. They do not replace testing, they're complementary. In a sort, if you perform tests, they show that your functional requirements are satisfied, and you use these tests to detect possible errors that you may have in either your requirements or your source code. So tests really help. Formal methods, they increase the confidence that no anomalous behavior will occur. So they may actually find additional faults that are not detected by testing. So as a result, you really need to do testing, and formal methods really is an additional tool, a complementary tool that can help you increase or decrease the likelihood that faults remain in your product. So of course, formal methods, they really kind of, formal methods use a formal model. The formal model really is either a representation of your requirements or a partial representation of your source code. So you really cannot use this to establish verification evidence for the target hardware. So you still need to perform testing on the target. So okay, uses of formal methods, of course, formal specification, formal derivation, formal analysis. We've already talked about this. Formal specification, I'm going to come up of certain lifecycle artifacts. That means certain lifecycle artifacts, like requirements, I'm going to represent now by a formal model, like what we saw in the PVS example earlier. Yeah. Also, you may actually derive certain lifecycle artifacts, like for example, if you want to verify the accuracy of the requirements, you can actually say, well, the formal analysis that I'm going to do is actually resulting in a set of results documents. Now coverage is it's a little difficult for formal verification, so we still need to worry about structural coverage analyses in a traditional sense like we do in D178C, but it's different if you start looking at formal verification. And typically what they're doing is they look at it like they have 4 alternative activities that they specify, which are kind of captured by cover, complete, data flow, extraneous. So cover means what you try to do is you try to find any missing verification evidence. So anything that you should have verified, like maybe the accuracy or compatibility of a certain life cycle item, with in cover we mean that we use the formal methods to detect if that's not there, if you have not done that. Of course, you can also do this to detect missing or incomplete requirements. In the analysis, you really kind of use the formal model and to actually, kind of write down these requirements. And of course, from the formal model, if you perform an analysis on it, it may result in you finding out that your requirements are really incomplete. Data flow, you can also detect unintended data flow, of course, and you detect code that doesn't correspond to a requirement. Yeah. So for example, if you came up with a formal model of some low-level requirements, you derived code from that, and now you can use maybe formal methods to find out if there is a match between the source code and the requirements, and if they're not, then you have to deal with that. Now, of course, in 61508 we already saw formal methods and exact formal verification as well as formal proofs are really, of course, formal verification is in 61508 recommended for SIL 3 and SIL 4, and of course it's highly recommended, formal proofs highly recommended for SIL 4.